Alright, so I haven't seen anyone pop into Zoom yet, and we're 5 past, so I'm going to start. If you've come into Zoom and you're waiting about, it's probably because I'm doing this instead. I've got the microphone separated from the laptop. It won't be as grindy as it was before, but you're still going to hear it in the background. And I'm working on that fully. Like I said, I'll take the thing apart shortly and go from there. Now what we're going to do, so we're going to look at projectile motion in its fullest. And so I'm just going to jump right in. Let's see here. Make sure no one's there yet. Alright, so I double checking the Zoom, making sure no one came and I missed them. Alright, so in the back of all this, what we want to remember is we want to think about and acknowledge and realize that as we do this, trig is going to break our vectors down. So a vector is something that has a magnitude and position, or direction. It gives an idea of the direction. And so this, in its basic point, could be some vector A, and its magnitude is its measured length. And its position can be some angle to the x-axis, and if this is the x-axis, or it can be represented by the xy components. Knowing the xy components relative to the origin does give you information on position. It's probably not the best for us to read and see what's happening, but it does give us all the information we need. In fact, in 2 dimensions, you'll need 2 numbers. You'll either need the magnitude, which we write with these bars around, at some angle, which I'll just call theta, or you'll need an x and y position. Now in physics, we'll tend to write A as whatever the component is in the x direction plus whatever the component is in the y direction. And that's these things here. We could say that was ax and ay. It's the positions in a Cartesian coordinate system for this. A lot of times in this book does this preference, it'll talk about the vector and its x component, which will be the number in there. So let's give this a value. Let's say this was at that's over about 3 and up about 4, 3,4. And so we could say ax was 3 meters, or whatever quantity I'm measuring, it would be unit consistent to that, and y would be 4. And the absolute value, or the magnitude of A, would be 3 squared plus 4 squared, square root. Right, sum the squares, take the square root, and that would give us 5 as the magnitude of this vector. And so this is what we're working with in the background, is vector things. Sorry, that was my phone, turning it off. The way we use these vectors are how we manipulate through 2-dimensional and 3-dimensional space. Now again, I showed you that we can strip everything down to 2-dimensional space. And so we call that motion if something is launched. My hand is crooked. Crooked hands here today. There we go. If we launch something, if we give it an initial velocity, some initial velocity vector, then the motion of that particle will be subject to the accelerations. And for most of our existence, that acceleration is due to gravity going down. And this is what we get coming out of it. And the motion is usually parabolic. Right, which means we can get some interesting things about it. In a parabola, at the top here, the velocity is only in the x direction. Right? So we'll say the v of y is equal to 0, but the v of x is equal to v of x. Like the velocity in the x direction always stays the same. And so up here when the y is 0, we can say it was moving upwards in the y direction, and now it's moving downwards. And so when it changes that 0 point, that's where we find the top, or the height of the flight. And so it's the same realization that we get when we were throwing an object directly up in the air, and we knew that its height was where the where the velocity term goes to 0. It has to stop and turn around. Well, the same thing happens here, but we still have this x component moving it forward. And so the height of flight, particle in flight, is still when the velocity is 0, but specifically the velocity in the y direction equals 0. And so we have this thing that will come about that will, I'm going to shut down the Zoom. If any of you guys come in, it'll send me an email. But I'm 10 minutes in already and no one's there, so I'll just shut it. So when we get to the highest point, the velocity in the y direction is 0. For all other points in the flight, we get a vector that's made up of 2 components. Okay, there's the vector itself. It'll have some component in the x direction and some component in the y direction. And without doing any mathematics on it, just looking at what will happen here, a couple things we can realize. If I were to do this from a flat surface, just like I rolled the marble off, so I'll roll 2 marbles. I'll roll a yellow one and I'll roll a green one. They're both on the same desk. So they fall off at the same time, but I'm giving no x velocity to the green one, and I'm giving a small x velocity to the yellow one. The only thing determining the up and down motion is the acceleration due to gravity, and it's exactly the same for these two. So the time is equal for yellow and green. The time of flight is going to be equal for yellow and green, even though the motion is different. And the only thing that differs the motion is this x component that the yellow one gets. So the green has no x component, there's no motion forward in the x direction, and it falls in the y direction, and it falls completely. Right? The y is equal to negative g over 2 t squared plus, I gave it no velocity, so why not? Right? Because this would be v in the y direction, but I gave it none. And so as it falls straight down and picks up y velocity. It'll be much faster at the bottom here. Okay, if we analyze the yellow one, there's a series of vectors that are made up of 2 components, vx and vy. Move tangentially to this. It'll have the x component here, and it will have the y component here. So oddly enough, the yellow one is going to have the same motion in the y direction as the green one. It has this extra x direction, which is the velocity in the x component times time, plus, well, we started at 0, so we don't need to write anything in there. And so that x position is derived from there. A neat thing about the y velocity vector and the x velocity vector is these y components of velocity will be the same. So for the green one, the velocity at the bottom, I'll do the green, so the green marble falling straight down. Now v squared equals v naught squared plus 2a delta, and we'll use y in this time. So I'm starting at 0, so that goes to 0. So the velocity is going to be the square root of 2g times the height. For the yellow one, in the y direction, the same physics is taking. I have no, whoops, I want the yellow one, not the green one. So I'm going to have v squared in the y direction is equal to the initial speed in the y direction squared, plus 2 times the acceleration plus the change in y. This is 0. It only has a component in the x direction, the yellow marble. And so the component in the y direction is equal to. And so they'll have the same component in the y direction. But this has an initial x component in the x direction. So the magnitude of this velocity is going to be vy squared plus vx squared, square root. While the magnitude of the green one is going to be this v squared, because that's its y component, but it has no x component. So this one has a greater magnitude of velocity. The yellow is moving faster in a straight line. And if we abstract that even further, I gave it energy. It has more energy than the marble that we just let fall. That push in the x direction is more than the other one has. It has more of something, and that manifests itself in having a larger velocity, a larger magnitude of the velocity vector. All right, let's look at some more of the motion here. Well, if I launch something upwards, it's going to go and reach its maximum height. Now at the maximum height, from there on out, all right, when y equals 0, it forms a parabola. And if this has no edge, it will continue to fall. There's something we can say about these two vectors. Since that v in y squared is equal to the vy initial squared plus 2a delta y, well, because of these squares, it doesn't have any information about direction. When we square a vectorized quantity, we square away the sign that tells us about direction. And so we're losing directional information, which means that these things will be answers in two places. And the places it'll be answers for us are where the height is the same. And so this initial vector and this initial vector angle, we're going to get the same thing over here. This is going to have the same angle mirrored, and the magnitude is going to be the same. So when I fall back to ground, if this is ground level, I will be at the same velocity, but what has happened is my y component. So remember, Vx is always the same, so we'll say Vx initial is equal to Vx final. And Vy initial is equal to the opposite of Vy. And so it flips in direction. I guess it'd probably be better if I put my negative sign here, right? Because the y component is pushing straight up. So let's look at the y component here. I'll do the y component in the right. So this is Vy. This is the component in the y direction. It's the projection of that vector on the y-axis. And there's Vy1, which is the same vector in magnitude but pointing down now. And that's what this acceleration component did, is up here it flips the y vector, so it's pointing downwards, and it speeds up. And when it's at the same height, they end up going the same speed in the same velocity vector in the y direction. And so we have this thing moving the way we need it to. And so we call this, when there is an axis where information is repeated on either side, we call it symmetric. And projectile motion is symmetric about the midpoints. And so we're going to have to find these symmetries in the problems to help us a lot of the times. What we want to do is we want to find these symmetries to help us. All right, so let's look at a very particular version of this. Right, and these are all vector equations. Let me just move down here. I'm going to clear the screen and so we're going to look at something that is why physics is taught in high school as part of the academic. There are courses that were considered to be important for military use: physics, chemistry, bio. An officer would need to know those, and so that's why they're the core of the science curriculum. Was there during the Prussian Wars, the early 1800s in Russia. It was decided officers needed to know these things. And one of the things from physics that comes out of this, though it's useful, animals have this encoded in their brain, especially animals that use projectiles or launch things or themselves at a distance, they need to know a range equation. But in most examples, we have a cannon or some type of military munition that fires with a known muzzle velocity. And you will find in Chapter 6, we'll figure out how to figure out the muzzle velocity of a gun using the bullet implanting itself in an object. But there's a way to measure the velocity, and so if you put a certain amount of gunpowder in here, you'll get a certain speed back out. And that will rise and then fall and hit a target. And that target is a range. And so what you want to know is you want to be able to figure out the angle to hit the target. And so that's called the range equation. And so what we're going to do is we're going to use these formulae to put together something that will give us the range equation, that will have us cycle through this space and create the range equation. Let me get my notebooks here. Sorry, I had the camera set up to work, but it was messing up the sound. And so when I talk without, I don't like these things staying on this like that. So, but let me, yeah, here we go. All right. So let's make the range equation work. So what we're going to do is we're going to break this down into components. And then we're going to put all the components together. We're going to need a little bit of trig to help us make it easier, but we can get there. So I am firing this with a known velocity, and it's going to go some distance. This is actually the x distance that we want to work for. And I have my gravity downwards. So in the y direction, I have negative g over 2 t squared plus v in the y direction, initial t plus y naught. That's going to be what governs my y direction. In my x direction, I have my initial velocity in the x direction times time plus where I start. So let's look at some things that are going on here. So the first thing we need to know is I know the velocity of the weapon. So I need to convert that to my initial velocities. And so that's going to be v sine theta, because sines give us our y components of vectors. And this is going to be v cosine theta. So if I know the velocity this would shoot in a straight line, I now know what my components will be when I shoot it at an angle. And so given a given angle, it will break down into these two components. Now I'm going to use some symmetry here, I think, to help me out. And I'm going to look at figuring out how long the time of flight is. Because I know over here I need a t. So I'm going to need to solve this for t. So let's solve this equation for t. Now I start at y equals 0. I start at the ground, and I go up and down. Well, over here y equals 0. So if I take this first equation and put in 0 for my ending position, minus g over t, t squared, plus v sine theta times t plus 0. So the range equation helps. I'm starting at 0, I'm ending at 0. So the beginning y and the ending y are 0. I'll rearrange this. This has a negative side here, so I'll make this g over 2 t squared equals v sine theta t. And I have t on both sides, so I'm going to divide by t. I get t, and I'm going to flip this over here, so I get 2v sine theta over g. And so this is my time of flight. Just time of flight. The time of flight is 2 times the velocity in the component in the y direction divided by g. So knowing my x, I can now find my range, or the range equation. So I know that my velocity in the x direction, v cosine theta, times time, but this is time. So it's going to be 2v sine theta over g. And if I put these together, I get 2v squared sine theta cosine theta over g. And this isn't too bad. You can put it in your calculator that way to figure out the range that this is going to go. But if you look on your sheet, sine times cosine, this thing here, is the same as sine theta cosine theta is the same as sine of 2 theta divided by 2. So I'm going to plug that in for here. The 2's are going to cancel. So I get v squared sine 2 theta over g. And this is kind of an important realization here, that this has this double angle. Because double angles are going to give us some weird things. So sine goes from 0 to 1 and then back down to 0. So in 90 degrees, sine is 1 at one place. But if I double this angle, so if I double this, so I can go from 0 to 180, when I'm at 45, I'm at 1. And when I'm at here, I'm at 1. So 45 degrees, I'm at 1. When I'm at 90 degrees, I'm back at 0. Well, that doubles and spreads out, and it ends up giving me a weird max and min. So if we look at this, if I shoot this at 45 degrees, the sine part is going to be sine of 90, which is 1. That's the biggest value sine takes. And so the furthest this will go is when sine is 45. All right, if you look at your unit circle, sine is the biggest at 90 degrees. And 2 times 45 is 90. So the furthest this will go, because this is going to be 1, that makes it, anything else is going to be less than 1. If I put in 30 degrees, I get 2 times 30, which is 60, and the sine of 60 degrees is square root of 3 over 2, which is less than 1. So the only time this gives the biggest value is when it is at 45 degrees. And so we can say the maximum range is when theta equals 45 degrees. Now this is, no wind resistance, no curvature of the Earth, all of that lovely-dovely stuff that we have to assume. And we'll see how to take the curvature of the Earth and the rotation of the Earth into account much later on. But it's possible, and cannons got big enough, the howitzers during World War II. You have one question later on that the gunboats on a battleship, because the ocean curves do have to take into account the dip of the ocean, just a little bit. But then what ends up happening is there are 2 angles here that end up having the same. All right, and so 60 degrees gives me, 30 degrees gives me an answer for 60, And 60 also has an answer that matches 60 degrees. And they have the same components. And so for every other range, other than the maximum, there are two firing angles. There's a low angle and a high angle. I didn't mean to drop that, sorry. And the low angle and the high angle only differ in the time of flight. The higher you shoot it up, the longer it's in the air. And that leads to like archery tricks. Someone will shoot a high arrow, it takes longer time, and then they'll shoot a lower arrow and they'll hit the same place in the target at the same time. And so this double angle here means that for anything but 45 degrees, there are two answers. And so let's look at one of these. Change color here. So, and I'll make 45 my midden ground. So we'll come here. And let's shoot at 30 degrees. So if I shoot at 30 degrees, a vector off at 30 degrees, that's going to arc. It's going to hit here. 45 is going to go further. But if I shoot higher than 30 degrees, I give more energy in the up direction, and it comes back down to the same place. And so the angle that has the same answer as 30 degrees on your signs is going to be, let's see, 45 is 135, 120. So that means 60 degrees. So if I shoot at 60 degrees, I'm going to go up much higher, but I'm going to land in the same place. And so 30 degrees has a smaller time of flight than 60 degrees. 30 degrees has an equal range, to 60 degrees. And everything but 45 degrees has the same, has two ranges. And you'll see that as you do the problems, that if you look at your unit circle and you double that angle, because double of 30 is 60 and double of 60 is 120, and if you take the sines of both of those, you get the same thing, because they're components that match back. I'm not sure, do I have that right? Is that 30 and 60, or is it 30 and 150? Let's see. 30 and 60, let's see. 30 is going to have that. Nope, it's 30 and 60. Yeah, okay. I had to get my calculator out to double check. And so projectile motion has this pairing, except at 45. But at 45 degrees, the range is the maximal. All right. That's the base of projectile motion, and that's probably one of the bigger equations we derive out of that. What I want to look at now is the beginning of relativity. And this is relativity in the understanding of Galileo. So relativity, Galilean relativity. Galileo. I'll just do this. Galileo Galilei. What Galileo noticed was if you were on a ship, and the ship was floating down a canal, and you throw a ball straight up, the ball comes back down. Straight down to you. And I guess this would be akin if you're sitting in a car, and you're driving down the highway, and you pick up your coffee, and you drink it, and you put it back down. The liquid's still in the cup. The liquid has no motion. But if I'm on the bank, and I'm watching the boat drift down, and I see you throw the ball up, and then you catch it, well, in the time you're drifting, your boat has drifted, I see the ball go up and back down to your new position. And so relative to me on the bank here watching this, the ball doesn't fall straight up or down. The ball makes an arc. And so we call this difference between two frames the relative motion. And relativity is a key with physics because everything is moving. And so when we make frameworks, we have to make frameworks that have some reference point. And so what we're going to do is we're going to take the idea of relative in one dimension, which is how we developed the idea of speed. Remember, we pegged something in one dimension as our origin. And we're going to look at that now in two dimensions where our relative nature can be vectorial. And we're going to pull those vectors out. And so what we want to do is label the object and frame. So we're going to, in our labeling, we're going to have a vector, and then we're going to have the object and frame. So what we can do is I could have water and the shore. So I have some water that's flowing by, and I could have someone moving in the water, someone swimmer. Now, to the swimmer, they're making motion in the water. And so they're moving with the water. Even though the water's moving, that's moving the swimmer. And so when we look at these, I can say the velocity of the water relative to the shore. And that's going to be this thing here. That's how the water flows by. And then I can have the velocity of the swimmer relative to the water, or the velocity of the swimmer relative to the shore. So the swimmer relative to water, swimmer relative to shore. And that creates a difference here. These things act differently, they're viewed differently, they're measured differently based off of your relative frame. And physics is what we measure, so we want to get this into a calculable framework. So let's I have a boat that is going to move straight. The boat's going to move in a straight direction. And that's the boat relative to the water. But the water has a current in this direction. So that's the water current. And so I get a vector. There's my boat relative to the water. And there is my water relative to the shore. So if I'm standing here on the dock and watching, I'm going to see the resultant vector. The boat's going to be moving straight, but because of the water moving, I'm going to see it move this way. And that's going to be the velocity of the boat relative to the shore. So I'm here, I'm watching the boat go out, and I'm going to see the boat travel this way. Now, it's a series of small motions. This is the vector of the velocity. The motion will be an arc, but its velocity vector will be in this direction. It'll be moving this way at a speed. Even though the boat's pointing this way, and it's moving this way with the water, because the water has a motion, these two things vector add, and vector addition. And so what we can say is the velocity vector of the boat relative to the shore is equal to the velocity of the boat relative to the water plus the velocity of the water relative to the shore. My vector additions. I added the two legs to get my resultant. And so relative velocities take into account the motions bodies are doing between each other. And what we want to do is we want that relative motion to give a resultant motion, a motion that we can make predictions out of. Because in a long time sequence, even though the boat's going this way, this will wrap about. All right, let's do an example of some relative motion. Let me get my examples out here. Not that page. That page, yeah. Okay, so I'm going to use the boat as an example here. And I'm going to have a boat in still water. If I took the boat and just had it go across a lake, the water's not moving, the velocity of the boat in still water is 1.85 meters per second. Right? So I take it on a lake, there's no current, and I throttle the engine fully, and I can move 1.85 meters per second. Now, if I travel it on a river that has a current, so the river has a current in this direction, so I'm trying to get from shore to shore, and the river's going down this way at velocity of the water relative to the shore is 1.2 meters per second. So I'm over here on the shore, boat's going to go this way, and so we'll put the boat here. The boat water is 1.85 meters per second. Now I want to find the vector that combines these. So I want to find the boat relative to the shore. What I'm going to see when the boat's moving this way and the water's moving this way, I add these two. Now I have to vectorally add these. So what I want to do is I'm going to make this my xy axis. And make that my 0. And so this is moving a negative 1.2 meters per second in the x direction. So the boat of the water to the shore is going to be negative 1.2. I'm going to need x hat plus 0 y hat meters per second. And the boat relative to the water is relative to the water is moving 0 in the x direction. So 0 x hat plus 1.85 meters per second y hat. Whoops. Y hat meters per second. And so the vector addition of this works out nicely. I'm going to be having a vector that's negative 1.2 in the x hat direction, because the x hats add together. And I'm going to be having a vector that's 1.85 meters per second. Whoops. I keep doing that for the y hats. It's like I want to get the units there. Y hat, and it's all meters per second. There we go. Now I can find out what that angle is going to be. And I can find out the magnitude of this. So if I look at that angle, all right, the angle is equal to the inverse tangent of my y component over my x component. Turn this backwards. Meters per second over 1.2 meters per second and that's roughly 59.6 degrees. Nope, 49.6, sorry. So this angle is 49.6. And so sure, I want to grab my calculator here. I did this in my notes and I want to double check it because I think my angle is a bit off. There it is. Make sure I'm in degree mode, which is I think what my problem was. Yeah, I'm in degree mode. And so second inverse tangent, 1.85 divided by 1.2. Yeah, I got 57 degrees. I thought I was right the first time. I went to 50. Sorry about that. 57 degrees. Always double check my calculator. And I see why I was doing a slightly different question earlier. And so that's the angle this would appear to move at, relative to the shore. Now what we can do is we can use these to solve problems and to figure out components that we might get. So I could have this same situation, same boat, same water, but now what the boat wants to do is it wants to make it straight across shore. So it knows the water is going to go this way. So it wants to point this way. It wants to point at some angle so it gets straight across the shore. And so now we have to figure out how we're going to point this way. So let's see, that's boat relative to the shore, and this is boat relative to the water. Now let me see. And so if I want these two things to come together, and so I can head to tail add this, then to find this angle, we'll do some trig here. So let's look at this. All right. So if the boat heads straight across the river, the current's going to drag it down here. So we're going to point up river so it brings it across. And so we know that the boat, this velocity is equal to the velocity of the water plus the velocity of the boat in the water. And so this angle here is going to be related to the opposite and the hypotenuse, because I know these. I know this one, and I know this one. I don't know this one. I don't know how fast it is going across that way. So, if I want these two to equal out, I want the velocities to equal out, I want them to cancel, I do the head to tail. The boat to the water, and that puts me in the same place I would be going straight across. I just need to know the angle. And so I go back to that Sakatoa. I have my angle, I have my opposite, and then I have my hypotenuse. And so in that case, sine of theta is going to equal my opposite, which is the velocity of the water to the shore, over the velocity of the boat to the water. Now again, to get, whoops, I made that much bigger than I wanted to. Oh, big, big. There we go, back. Ah. There we go. La 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 la. I wanted to slide down. So I want theta. I want to know the angle I'm going to aim at to get there. So I want to take the inverse of my sine. Do that to both sides. And so these inverses will cancel. So this is being left-handed. My tablet has buttons on the left side, and my left hand always bumps them, and one of them magnifies. So these will cancel, leaving me theta equals the inverse sine of the velocity of my water, which is 1.2 meters per second, over 1.85 meters per second. Now notice the units cancel, and this is unitless. Sine, the things inside a sine function the units should always cancel. They should be a ratio of things. So I go second inverse sine, 1.2 divided by 1.85, and I get the 40.4 degrees. And so if I were navigating this boat and I wanted to go directly across the shore, I've got to always aim 40.4 degrees away from where I want to go. I've got to always aim that way so that the water current and me getting directly across shore will add up. And so our triangles become important with relative velocity. All right, well, I've had no questions because no one has shown up. Those are the two main examples I wanted to get to, is relative velocity and projectile motion. What I really strongly recommend is as you're doing homework, ask me questions, and I'll put up examples around the questions you have. To me, this stuff's fairly cut and dry, but I've been doing it for years now that I have it in my pocket, and there are places where you're going to stumble and you're going to need to ask me questions on them. I will say get used to labeling things in a clear fashion. The object, the reference frame. The object, the reference frame. The object, the reference frame. And that'll help you build a little triangles. You have your little triangles on your paper, so you just line things up and then ask the questions. Toodaloo.